Well, we got a little snow here. So a little cold here. Had some snow last night, a little bit. It's melting pretty fast. This is class G we're going to be doing, and class G is the ideal gas law and thermodynamics. So we're going to derive, and remember when I use the word derive, put it in quotes, not a rigorous derivation. It's meant to help us understand how theoretical physics, the landscape, fits together. So we'll use Newton's law, F equals ma, or in particular the form, the change in momentum with respect to time. Calculate the pressure due to the motion of molecules bouncing off walls or the floor, in this case, we'll be using. And show that we can have a definition of temperature that's based on the molecular motion, the average kinetic energy of the particles in the gas. And then we'll introduce the first law of thermodynamics, which basically says that the change in energy of a system is equal to the energy in the form of heat that you put in minus the work that the system does when it expands and works on the outer environment. And then we'll look at little manipulations with thermodynamics and look at the big four processes. One where the volume is constant, the pressure is constant, and the temperature is constant, and then there's no heat transfer. So we'll be looking at that. And then we'll end up with one cool application, an engine, a cycle, thermodynamic cycle, and calculate the efficiency, how much work we can get out of the system compared to how much heat energy we put in. Hope you enjoy the class. We end with a touch of engineering. Chapter G, the ideal gas law and thermodynamics. Ideal gas law and thermodynamics. G1 review. I included this page that we already covered in our first class that discusses the ideal gas law. There were a couple pages there that we did. So that ideal gas law, PV is nRT, where this is the number of moles N, or you could use the number of particles, and then lowercase k, T, the Boltzmann constant. G2, derivation. Let me put the quotes there, since we don't mean our derivation to be rigorous derivations, but to help us understand how physics is connected. Derivation of the ideal gas law. We're going to use Newton's law, F equals ma, for the change in momentum with respect to the change in time in this derivation. So we have Newton's law, F equals ma. Let's review some of the things we've looked at. We've looked at Newton's universal law of gravitation, and we have looked at Coulomb's law, where in this particular case, this K is 1 over 4 pi epsilon naught. That's the electric constant. Some folks might write a little e, a subscript to go with this K. And then what we did is we used the rotation matrix to understand relativity, the Lorentz transformation. And then we used relativity and Coulomb's law to help us understand E&M, or electromagnetic theory. And then out of E&M was born optics, light, the speed of light. So we're going to see here that F equals ma is going to get us a way to understand thermodynamics. And we're going to start with the ideal gas law. Now we're going to need probability, because when you have zillions of particles in a gas, you're talking statistics. Let's look at discrete statistics, where, say we had different velocities. That could be, we had so many, this is the number, and we'll divide by the total number. This is the number that have velocity I. And say more have this velocity, and more have this velocity, and so if this was discrete, that'd be kind of like having like you have exam scores, and this is the number of this grade divided by the total number of exams. So you might say like 1/3 of the exams, have this grade, then over here, this high score, this is the score, there'd be a fewer amount. So it's important to note that if you sum up all the fractions to get all the exams, you get one. That, in other words, you can look at that as just if you summed up all the individual exam papers, you would have n exams. And if you divide by big N, then you would get one. Now with velocity, you have a continuous distribution. So if you have a function of here that say that the probability distribution does something like this. And the way this one works is if you take a little strip, dv, then the probability that the speed is between v, because this would be the v, and this one over here is v plus dv. So if you're in this range, that's given by the area. Sometimes we just go ahead and write that as the height times the width, a little strip like this. And then if you were to integrate over all the velocities to get the area under the graph, the complete graph would have area 1. We're also going to need a definition of pressure, which is the force per unit area, newtons per meter squared, pounds per square inch. Sometimes they say PSI, pounds per square inch. And the force, F equals ma, but in more general, it's the derivative of the momentum with respect to time. So this little p is momentum, and this capital P here is pressure. Now we're going to consider particles hitting the floor of a room, and I'm going to look at particles that have a certain speed, velocity, say v, coming in at this angle, theta, with respect to the vertical. And here we could have, we could just say this is a little delta A, delta area down there at the floor. and we'll say this is a dl, and the particle right there at the edge coming with velocity v, the time it takes that particle to get to the floor, that's going to be your dl dt in a time delta t to go from there to there. Now, you could have written this as a delta L and this as a delta T, and then you're going to take limits. But we'll just go ahead and leave this one as a delta, capital delta, and this as differentials, a dl and a dt. So what's the probability of particles coming in at that angle? Well, if we look at, say, here, a cone, okay, where we're coming around like this, and say here, like a little delta, a little strip here. Little ribbon. So there's theta, and say we're looking at an R here, and then this is a little d theta. And you can put a radius here. This is going to be R sine of theta, the right angle there. And this little thing here, when you do this thing here, this is R d theta, so R d theta. You basically take R and do a little d theta delta in there, and then you get this little arc length. So what we're looking at here is the probability distribution. I'll call it G, and this is so that the particles between theta and theta plus d theta, just like we did a continuous case with the velocity, this would be equal to, I'm going to go ahead and look at this as a little ribbon strip that's going to whip around. So it's 2 pi r sine of theta to get me around, and then I take a little r d theta, 2 pi r sine theta is my circumference, and then if I take a little thickness there, then I have the area of my ribbon, and I need to divide by, for the probability, the whole dome. If we have the whole dome there, all the angles, that would be 2 pi r squared. This is half of the surface area of a sphere, because this is a semi, a half, a dome, it's a half. So then the 2 cancels, the pi cancels, r squares cancel, and you get this cool formula, sine of theta d theta. Now we can check to make sure that if we integrate here, we're going to be integrating from 0 to pi, because this whips around. If we go from 0 to pi over 2 rather, we go from 0 to 90, 0 to pi over 2, of sine of theta d theta. This is going to get us minus the cosine of theta from 0 to pi over 2, because the derivative of the cosine is negative the sine. And when you put in pi over 2 for the upper limit, you get 0. And then when you have the lower limit, you're subtracting. So you really have like a 0 minus 1. And that's equal to 1. So that's what it's supposed to be. Okay, so then what we do is we set up for the little bit of pressure that's going to be down here. So we're going to say the little bit of pressure due to this case, this slant case, we'll have the number of particles in the room divided by the volume of the room. So this is the number density. And I need to multiply by the volume of this. Since I'm only looking at this element. Well, the volume, see, if it were straight down like this, the volume would simply be the dl times the delta area. But it's slanted. So since it's slanted, like if you look at this here, you're basically looking at this this length times this little width. But see, that angle is complement to this one, so this angle is the same as this one here. And delta A, if you take the delta A and you go with the cosine, that's going to get you the area that's relevant. And if you should bring this theta to 90 and flatten it out, then there is no area, and the cosine of 90 is 0, so that like checks out. So therefore you want delta A cosine of theta dl. Now the probability that the speed is what we say it is, that's going to be, now with the, I'm going to put a 1/2 here and I'll explain why. If we have the probability that we have speed v and v plus delta v within that range, half of them will be going the wrong way. Half going down, half going like slanted up. So I want the 1/2 there. Then the probability that they're between the angle theta and theta plus d theta is going to be this sine of theta d theta. This is a nice setup in theoretical physics here. And then I need to have here for the force. But what is the force? When a particle hits here and bounces back, like what's the change in the momentum? Well, if you came straight down, say with mv, and then you bounced back up, then you would have here, if you think of this as a minus mv coming down and a plus mv going up, when you take the difference, the change would be 2 mv. You basically stop, mv had to go to 0, and then it had to bounce back and go to plus another mv. But here, what you're doing is you're coming in, see, at an angle, theta here, say phi. So we're coming over here and we're like redrawing this, showing the theta, showing the, say, the angle coming in, and then this is the complement, phi. So really you want the component of velocity that's going to hit that ground and bounce. That's what's going to contribute to the pressure. This component's not going to really, it's not going to add any pressure. If anything, maybe a shear force, but not the pressure. You want the force coming down. So you want here, this is mv, you want the sine of this angle, which is the cosine of theta. So really you want 2 mv cosine of theta, and then there's going to be the dt, the time frame for that to occur in. And then you need to divide here, since that's the force, it's a change of momentum, you want the force per area. So you want to divide by the area. So really this is the key part right here, that one particle is going to give a change of 2 mv cosine theta in the time frame delta t. And then you're going to divide by the area. This is going to get you the probability that you indeed have that angle. And this is the probability that you indeed have that velocity. And then this is the number of particles that are available with those conditions. So it's a nice theoretical setup. And maybe at this point, we take a second to just give credit to the marvelous book by Derek Livesey on atomic and nuclear physics, where I got this derivation. Beautiful work there. And he also derives a Dirac equation in there. This book was used by like sophomores in physics, and Livesey helped inspire me with this course to put advanced concepts in a course that someone like, say, a sophomore could take. Okay, so now it's a matter of just collecting everything. So the dp, you know, if it was your preference to use a delta t there, you could have, And you could have had a delta, you know, in other words, a capital delta there. It doesn't matter. So here we have N, and we have, say, the mass, and let's divide by the volume. And then here I'm going to put next dl dt. So we can maybe check off what we've got. We took care of that, we took care of this, now we're taking care of the dl, this dt. Then we notice that we can take care of this 1/2 with this 2, it's going to cancel. Then here we would have v from over here, this v, and then f of v dv takes care of that. And then over here, angle stuff, we have a cosine and a cosine and a sine. So we would have a cosine squared sine and the d theta. And the last thing here, this delta A, they cancel. So like everything's checked off here. So this is what we got. And dP then equals Nm over the volume, and that's going to get you a v squared, another v. That's a v, so this is going to get you a v squared. And then here we'll have the cosine squared sine d theta. Then it's time to integrate. So to integrate here over everything would mean we'll go from 0, and since this is pre-relativity, we'll go to infinity. All right. The probability of particles traveling really fast anyway is going to be 0. It's going to approach 0. You know, here this thing tails, so it's going to be approaching 0 as you get super fast. And then here we would have 0 to pi over 2 cosine squared sine theta d theta. So this thing here is going to integrate as a minus cosine cubed over 3. If you take this derivative, a 3 comes down, cancels. You get then cosine squared, and then the derivative of the cosine is negative the sine using the chain rule, so you get that. And here, this would be minus, when you put in pi over t gets 0, and then subtract, when you put in 0, you get 1, so that's like a third, and then the 2 minus signs cancel. This is going to be 1/3. This is the average of v squared. See? Just like if you were taking an average of something, you would, put your score here, and then the probability that you have, that value, and then that comes out very easy. So you really have the answer here. P is N over V M V squared, that's average, with the 1/3, which we can write, well, let's write this as PV, is N over 3 MV squared bar. Like we're getting there. Now, the kinetic energy, remember, is 1/2 mv squared, and the total kinetic energy would be 1/2 mv squared average for all the particles. So that means that PV is equal to, here, by using this idea, let's go ahead, just write down N over 3 mv squared bar. It's related to the motion, kinetic energy, and we're going to make a definition here. I'm going to call this N, and everything else KT. In other words, this definition of temperature, and this absolute temperature, because we could have velocities go to 0, and also we have temperature is defined by more energy, more motion. So you have a balloon, for example, and the molecules are traveling with greater average speeds, then there'll be more pressure in the balloon. And then we could also define this as the number of moles times R times T. And by doing that, what we are saying is that 1/2 mv squared, the average, if we look at this thing, this has to be 3/2 kT. So the way to see that is if you were to bring the 2 over to the right, the 2's would cancel, and you'd bring the 3 down here, you'd have 1/3 mv squared bar is kT, and like that's what this is. We're saying the 1/3 mv squared bar is kT. So we could have actually written that down first. That might have been better to just start with that. And then say if you put the 1/2 here and bring the 3 over here and put the 1/2 on the other side, then you get this. This would have been a little more, that's a little more elegant, so let's do it that way. So the energy related to the temperature. And you could think of this as 3 dimensions, and there's a 1/2 kT for each of the 3 dimensions, like the Vx squared, the Vy squared, and the Vz squared. You know, looking at those averages. G3, the first law of thermodynamics, and that is that the change in energy, we use U for energy in the system, is equal to the heat that's put in and minus the work that it does. And to understand this, we're going to draw little graphs where we have, say here, this is going to be volume, and this is pressure. So volume 1 and volume 2, and pressure. And here at this pressure, if we have a pressure that does an expansion, so we can consider this, say, where you have, say, here, some like piston. All right, say some piston here. And say the pressure, the gas expands. So say the gas expands and goes from volume 1 to volume 2. So, you know, at pressure due to the pressure P. That's the force. So then the work is the force times the distance, and the force is the pressure times the area. And the distance here is D. That it moves through, that corresponds to this volume change. So if you have the area times this distance, this is going to be your change in volume. So this is the change in volume. Perhaps it's best not to put the D there because this is more of a delta volume. It's better to put the D over here, since that volume really is this volume, and here it makes sense to put the D. So like the D should be there, and then here this is delta volume, just to keep the graphs neat and precise. So now we have an interesting concept. Little c at constant V, this is the definition, is you dump heat into a substance and measure its temperature at constant volume. and that's called the specific heat. So I like to use this in conjunction with the first law of thermodynamics and get some conclusions. So the change in Q, the heat, I can then put the change in energy plus then the change due to the work. But see, this is P dV as figured out up here. So in this particular case, constant volume means delta V is equal to 0. So that means delta Q at constant volume. See, it's going to be just a delta U. But we know what the U is. The U is N particles times 1/2 mv squared, the average. And we know that this is going to be 3/2 kT, and there's an N in there. So let's N is in there. It can be written also as 3/2 nRT. So this definition would be 1 over the number of moles. And here I want delta Q over delta T at constant V, which is going to be the delta U over delta T, since the equality here. So this is 3/2 nR delta T. A delta U is just going to have that delta T, and this is going to work out when you divide by delta T. This is going to work out to be 3/2 R. The specific heat at constant volume is 3/2 R. That's kind of cool. And here, if you punch in a lot of heat and your temperature doesn't go up hardly at all, we say you can hold the heat because you're dividing by a small number, you get really super large. But if we put in some heat and you go bananas on your temperature, then this is a lower value, which means that you can't hold your heat. So delta Q is delta U plus P delta V. This is the way of writing delta Q. We already wrote that down once already. And this is 3/2 nR delta T, since we know what U is in terms of T. And that's always true. Then we have this equation, and we can write this as N. Remember, 3/2 R is C sub V, so we can do that, plus P delta V. And then there's a cool little trick. Since PV is nRT, what you do is you play this game. You take the delta of the product, and that would be here. You would take the delta of the first one, times V, plus P times the delta of the second one. But that also leads to nR delta T. So you always can get that too. So we're going to write this down here. P delta V is nR delta T minus this one, V delta P. Now the reason why I want to do that is because when I use this equation now, delta Q, actually in this second one here, it's going to be just copy. I'm just going to copy N CV delta T, but then for the plus P delta V, I'm going to copy this one down here. And this here, there's a little factoring going on there. I take the N out, then I have CV plus R. and take the delta T out. And then if I want the constant pressure case, where it's specific heat at constant pressure, where I'm looking at dq, constant pressure, dt, you can put the little p there, or you could put the little p down here, you know, one or the other. So some folks like to just take that derivative and put the p down, it means constant. Or I can put it up there. See, that means this is going to go to 0 at the constant pressure. And I have 1 over n, and then I just have this, n CV plus R delta T over delta T. So I get this cool result that this is CV plus R. It's a nice result. And that would mean here, since this one is 3/2 R, CP is 5/2 R. Very nice. So some manipulation here with ideal gas and the first law of thermodynamics and some definitions of specific heats. Okay, now we go to G4 for thermodynamic processes. First one, isometric, sometimes called isochoric. And this means constant volume. In other words, delta V for volume is equal to 0. So let's look at that. If we do the work, which is to integrate PdV, as we saw in the earlier section, since the volume doesn't change, 0. No work is done. Gas has to expand to do work. Or if you want to do work on the gas, like a negative work, from the gas's perspective, you have to then compress it. That's done. 2, isobaric. I remember isobars in meteorology or weather maps, lines where the pressure is constant. So this is constant pressure. So that means delta P is equal to 0. Okay, well now we have that nice case that we looked at earlier, where if we have the volume and here the pressure, and it's constant along this line, and say we started with volume 1, and it pushed out the volume 2, then the work is going to be the area, see under that graph. Watch, V1 to V2, you want P dV, but since the pressure is constant, I can pull it out of the integral sign. That's what makes this reduced to a nice formula, constant pressure, because you can't do this in general when pressure is changing. And now it's very easy to do the integral. You're just going to get P, V2 minus V1. That's just going to integrate to V, then from V1 to V2. It's just the difference. So that's nice. 3, isothermal. Here, you want constant temperature, isotherm. A line or a curve where the temperature is the same. So delta T is equal to 0. And let's look at the work again. If we look at the work and we integrate from, say, volume 1 to volume 2, PdV. Now the pressure is not constant, but we're going to use the ideal gas law. PV is nRT, so nRT divided by V is solving for P, all right? Because we're using the formula PV is nRT, so P by itself is nRT over V. And since the temperature is constant, you can't do this in general, but since the temperature is constant, I can pull it out with the constants. Then I have 1 over V dV, and this is the natural logarithm of V. And we go from V1 to V2. That'll get us the log of V2 minus the log of V1. And remember how logs work, that's the ratio, the log of the ratio. So the work is nRT, T is constant, you get this nice formula. Now we go to 4, and that's adiabatic. And for adiabatic, no heat flow. So in this case, delta Q is 0. And this one requires a little bit of work. This will take us a little bit of time to derive. So let's go back and look at our formula that we did earlier. Delta Q we had is delta U plus P delta V. We used that recently. And this can be written as N C sub V delta T, we saw that earlier, plus P delta V. All right. And we want to remember that U can be written as 3 halves nRT. So then delta Q is N CV delta T plus this equation we had earlier. We're simply copying down over again. You should take a moment now to find this equation written in your notes from just moments ago. So just take a second to make sure that this equation you already find in your notes, that we did this. And then at that point, we set the delta P to be 0, but here this was general. We had that in general. And also take time to make sure that you find this in your notes and this one, CV is 3 halves R. Because when you put the delta U in with these two equations, you get this. Since the 3 halves R becomes CV, the N is there and the delta T. So just make sure, it's important to do that because these equations are hard to, like, all of them, to keep them all in your mind. So you want to go back and check that. So now the question is, we have a couple equations here. We have this equation and we have this one here. NCV delta T plus P delta V. So we have these two equations. And since delta Q equals 0, I can set these equations to be equal to each other. And I would like to remember when you add these together, that was the C with the little p. That was a specific heat at constant pressure, which was the 5, remember that was the 5 halves R. This is 3 halves R, and then when you add, you write the 5 halves R. So that makes the equation a little easier for me to write down. So if I do that, then N CP delta T minus V delta P, that's equal to 0. And this other one's equal to 0, NCV delta T plus P delta V is equal to 0. So let's go ahead and, let's not set these equal. Let's do something else. Let's do this. Let's do N CV delta T equals minus P delta V. Just subtract this on the other side. Then for this other one, let's go for this one, N CP delta T, is this one. Put this on the other side, is V delta P. All right, so now let's divide the equations. So we have, say, this one on top, N CP delta T over N CV delta T. And there'll be a minus sign here. This one's on top. This one's down here. And that leads to CP over CV is minus V over P, and this is a dP dV. Now let's let this be, by definition, gamma, which will actually, for the ideal gas, be 5 halves over 3 halves, which is 5/3, but let's just keep it as gamma. Then we have gamma equals V over P dP dV. And then we do a calculus. dP over P is equal to, there's a minus sign here, is equal to minus gamma dV over V. So we just simply collect the V's on one side of the equation to P. So dP over P, that's here. And then if I put the dV over here and the V underneath at the minus sign, I get this. And now I can integrate from P1 to P2 minus gamma, V1 to V2. This is 1 over V. These integrals are going to get natural logarithms. P1 to P2 minus gamma log V1 to V2. And this will be then the log of the ratio, because you subtract them and then you do the division trick like we did earlier. And then what we do is, we know this trick. We can put the log here with the minus gamma, because when you take the log of this thing, you pull that minus gamma down and have the log of the rest of the stuff. So that means that P2 over P1 is V2 over V1 to the minus gamma. And that means we can flip this and make the gamma plus sign like that. And then we can bring the V2, put the 2's on one side of the equation like this, and the P's on the other side of the equation like that. And we were basically showing that PV to the gamma is equal to a constant. Nice formula for an adiabatic system. Isn't that nice? G5. Let's go engineering here. An engine. Let's look at an engine problem. And we'll assume our engine has an ideal gas. PV is nRT. And the engines have cycles. They repeat. So let's give a PV diagram. There's your pressure, there's your volume. And let's say here is a 1 and then double the height. This is P naught and 2P naught. And then we'll come over here and say a volume and then double. In other words, volume V naught and then double. And then we'll say here, this is just to give me a reference so I can sketch it better, like a graph paper thing. And say here, I'm going to compress the gas, and then there'll be some kind of fuel that'll like explode and then make the gas expand and then we'll compress it and repeat the process. So say we have A to B to C to D. And see, when it expands, it's going to do all this work, the area, but when I compress it, I do this work. So really the net work is going to be that one, because when I compress it, I'm doing negative work. It's costing me energy. So that's going to be the work done. And the ideal gas law means P naught V naught is NR T naught. And that gives us all information at point P, point B. So at point B, you have temperature T naught. But notice what happens if the volume doubles. Well, if the volume doubles, like you're at A, if your volume doubles like this, then your temperature at A has to be 2 of the T naughts. So this temperature here is going to be 2 T naught. Here, same trick. If you double the pressure, this will be 2 T naught. And over here, I have 2 P naught and 2 V naught. So this is going to be 4. So I'm basically using this formula. See, at this point D, I have 2 V naught and I have 2 P naught. Well, that's going to give me here, if I did that and have a 2 there and a 2 there, that's a 4, then I better have a 4 in front of this thing. So that's where we got that. So we have all the temperatures. T naught, 2 T naught, increase in temperature due to the interactions, say, in the engine, and then here, an expansion. And then the compression, and then, well, actually, the compression is this way here. This is a drop in pressure. So if you look at these things, you have really, this is an isobaric, constant pressure, then you have an isochoric, constant volume, then an isobaric, an isochoric. So what we do is we make now the master table. The master table where we have here the change in internal energy, which is going to be 3/2 NR delta T, and then the change in the heat, which is the formula we had before, delta U plus B, P delta V, and then the work is a PdV. So this is a nice problem that just like explains everything with the application. And then we can say here, let's look at going from A to B, and then from B to C, from C to D, and from D back to A to complete one cycle of the engine. So if you go from A to B, your temperature went from 2 T naught to 1 T naught. So that means your delta T here is a negative T naught. So this is negative 3/2 NR T naught. So just think T naught times 2, and then we go down to T naught. So the delta T is a negative T naught. Here you do the flip. You're going from T naught to 2 T naught. So this is going to be plus in the energy. Then to go from 2T to 4T is a 2T. So if you put a 2T naught in there, then you'll have a 3 NR T naught. So let's do that one again. To go from C to D, your change in your delta T in going here is going to be equal to 2 T naught. So you put in 2 T naught there, the 2's canceled, and you get 3 NR T naught. And then for the last one, you go from 4 to 2. That's the reverse of the one we just did. So this is minus. And if you do the check, and you add these up, you get 0. Like they cancel out because you're back to your starting point. So like there's the total change in the energy going to be 0. Okay, now we look at what else we can do. Probably the work's the easy one here. When you go from B to C, you don't change the volume. So from B to C has to be 0 work. And if you go from D to A, you don't change the volume. It has to be 0. Now, when you go from C to D, you're doing your work. But what's the pressure? It's 2 P naught. What's the change in volume? 1 V naught. So if you look at this thing, you have here 2 P naught, 1 V naught. And if you then use the formula, you know, P naught, V naught is nRT naught, and there's a 2 in front. This is 2 nRT naught. Now, when you're doing this first one from A to B, you're losing. You're going down by, it's negative because you're compressing. So you're basically going minus P naught V naught. But remember, P naught V naught is nRT naught. So this is minus nRT naught. So we have them all. All right, everything's done. Except this one. But then this one I can get by the formula. You take this column and add it to this one. So if you do that, just like add this delta U plus P delta V, this is a minus 3 halves, minus 1 is a minus 5 halves. So this is a minus 5 halves nR T naught. Then if you add these two together, you get just the 3 halves nR T naught, since you're adding 0. For these two, you get 3 plus 2 is 5. So this is then 5 nR T naught. Then if you add these two, you get minus 3 nR T naught. It's fun. It's like a puzzle. And then what you're really after is you're after, like, what is the work I get out for the heat that I put in? So the work, you know, this is the net work that you're doing, is the area inside here, which is going to be P naught is 1 dimension times V naught. So P naught V naught, and that's nR T naught by our setup here. And then the question is, what about the heat? Well, let's look at the heat that goes in. So this would be like it's the positive heat. It's like the plus one. So that would be here. I need to get this, just like from my fuel, and I need this one. Now, I'm not worried about the waste. That's the other ones. This is what I'm looking at. So really, the Q that's going into the system are going to add 3 halves plus 5, which is 10 halves, R, there's an N in there, nRT naught. So this is 13 halves, see, nRT for this part. So that means for the efficiency, I want the work, this is the net work that I'm doing. I can emphasize that by putting net. And then this is the heat that I'm putting into the system. And this is going to be nR T naught divided by 13 halves nR T naught. Now, you know, this is going to cancel, and I'm going to flip this to be 2 over 13, and that is cool. That is my efficiency. And you expect it, of course, to be less than 1. You're not getting anything here for free. And that's the efficiency of that engine. 2/13. It's like the fraction of the energy we put in that we're going to get out as work. Like whatever, like driving a car, or, you know, or some kind of machinery, or, you know, something that's a cycle. So, nice engineering application here to end our class.